everyone, and thanks for watching Edupedia World videos. In this video, we begin our study of various optical instruments beginning with microscopes. Now, before starting the study of microscopes, there is one important concept which you need to study, and that is the concept of the apparent size when we look at an object. Now, most of you have had this experience. You know that the farther away an object is, the smaller it looks to the eye. In fact, many times if you just take your pencil and you put it against your window, you'll see that your pencil looks to be bigger than a tree outside. That doesn't mean it's actually bigger, but the apparent size of the pencil, because it's so close to your eye, seems to be bigger than the apparent size of a tree, even though a tree is actually much bigger. So the way this is decided is using something called the visual angle. And the visual angle is the angle that an object subtends on the eye. So let's say this is the eye, this is the lens, these are the ciliary muscles. I'll not go into the discussion of an eye too much. You can just look at a figure in your textbook. There's not a lot of mathematics or physics there. It's just a diagram and some labels. These are ciliary muscles, this is the pupil, this is the cornea, this is the eye lens, this is the retina, and so on. So the important thing for us is that the eye has a lens, and the focal length of that lens can vary. It has a minimum value and it has a maximum value, but it can vary between those values. And it always varies such that any object kept anywhere will ultimately have an image formed at the retina. Right. So we know for a lens, 1 by V minus 1 by U is equal to 1 by F. Right. So if V has to stay the same, if we want B to be at a particular value always, the image distance, then as U changes, F has to change correspondingly. And that's what the eye does. Every time an object comes at a different distance, the F changes accordingly such that the position of the image is here, and this distance is around an inch or so. We don't need to know what exactly this is, but the image has to be formed at the retina, so the focal length changes. Now, if this height of the object is h, and this distance between the eye and the object is d, then the visual angle subtended by the object is h by d. Right, a ray might go like this, and it might end up making an image like this. Right, other rays parallel and going through the focus and so on. We won't draw the ray diagrams right now. Okay, so the visual angle is h by d, and this determines the apparent size. So the greater the visual angle for an object, the greater its apparent size will be to the eye. So if you keep a small pencil but you keep it very near to you, and you keep a big tree but keep it really far, then the distance could possibly overcome the size, and the visual angle of this h dash by d dash might be smaller than the visual angle by this. If this is h now and this is d. So the bigger the visual angle is on the eye, the bigger the object looks to us. Right. And this is a concept which is used in many optical instruments, and we'll start of course with the simple microscope. Now there are a lot of ray diagrams in this video, in this chapter as such, microscopes and telescopes. So I'm just going to show you the standard ray diagram which I've downloaded from the internet, and then I'll try to explain it as we go. So this is the standard simple microscope. You can see it's a simple convex lens of a certain focal length, and an object is placed in between the pole and the focus. And we already know that when an object is placed in between the pole and the focus, then we have a virtual and erect image that is created of the object. Right. I couldn't find a better figure on the internet, but this is not supposed to be 2f1 or C. It can be anywhere. It might be for a special case at C, but it can be anywhere in this region. Right, so don't focus too much on this. All you need to worry about right now is that you keep an object and then you put a convex lens in front of it, and you look through the convex lens. The object, the image will appear to be erect and of a greater size than the object. Right. Now there are two possible configurations which we'll do for microscopes and telescopes. One is normal adjustment. And normal adjustment means that the rays coming into the eye are coming parallel to each other. Right. So for example, if you look at this particular image, these two rays are not parallel to each other. Right. Therefore, when you project them outwards, you actually see an image. However, if this object, instead of being kept between the pole and the focus, was actually kept at the focus, then these rays would be parallel to each other and we would see an object to be really far away. And that configuration is called normal adjustment. So in the normal adjustment, the image is formed at infinity. And because the image is formed at infinity, now I'm just going to draw the eye lens like this instead of the whole eye. And let's say this is the retina where the image needs to be formed. So parallel rays will meet at the focus, right? And this has to be the focus because the image has to be formed here. By the way, this image and this image are different. I don't want to be confused. This image is the image formed by the magnifier. We put magnifier is another word for simple microscope. We put a simple microscope in front of an object and look through it. We are not looking at the object. We are looking at the image of the object, and that image itself is forming an image on our eye, right? So let me make that a little bit clear. This is our object. This is the image of the object as formed by the simple microscope. Now this image will actually make eye rays go into this eye, and they'll form a second image on the retina of the eye, which is how we'll be able to see things. Right. So if this image was at infinity, that means if this object was at the focus, then the rays coming into this eye would be parallel. And it will seem to us that the image was located at infinity. The image which creates a second image on the eye, mind you. Right. So in that case, this distance has to be the focal length. For any other case, let's say the object was at a certain distance. In that case, the focal length would have to be less than that in order to make the image here. Right. So the greatest focal length is when the image is at infinity. As the image starts coming closer, the eye starts to decrease its focal length. If the object is just very near here, then we would need to have a strong focal length for it to make an image here. A very small focal length, in other words. So what is the property of normal adjustment? The eyes are least strained. Right. So the closer an object is to us, the more strain we have to put on our eyes to see it, because the focal length changes by a greater amount. But if we look at an object coming from infinity, or let's say we look at the moon, the rays coming almost parallel to us, in that case our eye is the least strained to view this object. The eye will never have a focal length greater than this distance, right? But it will have a focal length exactly equal to this distance if the object is coming from infinity, if the image is coming from infinity. So this is the first case we'll study for simple microscope, compound microscope, and for different telescopes. The second case we'll study for all of them is when the image is at D. Now what is D? D is called the least distance of distinct vision. Now it is also sometimes called the near point of the eye. So every eye has a specific far point and near point. The far point is the furthest distance an eye can see clearly, and usually it's infinity. However, some people can develop some problems in the eyes and they need spectacles in order to correct them, and we'll look at the various defects later on. But right now we need to know that the far point is the furthest distance an eye can see, and for a normal healthy eye it is supposed to be infinity. The near point, or the least distance of distinct vision, is the minimum distance of an object for which an eye can clearly see the image. Now if you take your pen and you keep it really close to your eyes, then you won't be able to see one distinct image, you'll see two separate images. Right? That's because you cannot clearly focus on the image, and that is because that object is closer to you than the near point of the eye. For a healthy eye, the near point, or the least distinct of distinct vision, is taken to be 25 centimeters. That means most people cannot see something when it is closer than 25 centimeters to them. You can see it, but you can't see it properly. You can't make a focused image on the retina. Right. So the image could be at infinity. In that case, the property would be that the eyes would be least strained. Or the image could be at the least distance of distinct vision, in which case we would actually see a greater visual angle, but the eyes have to be most strained. Right, because if this is the eye, you keep bringing an object closer and closer, there'll come a point when this focal length will be a minimum value and it won't be able to decrease below that, and you won't be able to see an object kept near that have its image formed clearly on the retina. So when you are at the least distinct of distinct vision, the focal length of the eye is minimum, and in that case the eye muscles are maximum strained. Right. So let's look at both these cases for a simple microscope. For a simple microscope, this is a generic case, but if we look at the case for normal adjustment, this object will be put here at the focus, and it will have rays which just pass through this focus, and the other one will go like this, undeviated, and they'll both be parallel. And when we take them backwards, we'll just see that the image is formed. I'm not able to make straight lines or PowerPoint, so I apologize for that, but we'll be able to see that the image is actually formed at infinity, right? And the eye will be least strained, and that will be called normal adjustment, right? Now, the characteristic for a simple microscope is the angular magnification that it produces. Now, up till now, we've been talking about linear magnification. Why angular magnification now? Because now we're looking at objects as they relate to being viewed by the eye, and for the eye, the height of the object is not important, the apparent size or the visual angle is important, right? That's why we'll focus on angular magnification. The definition of angular magnification is simply the visual angle of the object where the object is kept currently divided by the visual angle if the object was itself kept at the least distance of distinct vision, right? Not the object's image being at the least distance of distinct vision, but the object itself at d, right? That would be the normal case. And so if an object of height h is kept at a distance of d from the eye, then the visual angle it would subtend is h by d. So this is what the visual angle would be if there was no magnifier and we kept it at d. However, if there is a magnifier or a simple microscope, and remember right now we're talking about normal adjustment, then we'll talk about, whenever I say A, it will be normal adjustment. Whenever I say B, it will mean that the image, because of the microscope, is created at D. Here the object itself is at D, right? And that will be same for both of them. Great. Now what is the visual angle in these cases? That's what we need to find out. So if you look at this image, if we keep an object here, the height of the object is h and this distance is f. If this angle is theta, then this is the angle which both these parallel rays will make with the horizontal, and so this is really the angle which will be subtended on the eye, right? So in the case of a simple microscope in which the image is formed at infinity, the angular magnification produced is h by f divided by h by d, or d by f. We can see that if f is less than d, then the angular magnification is greater than 1, which is what we would want. So for a simple magnifier, we would use a convex lens which has a focal length less than the least distance of distinct vision. Now what would happen if the final image is formed at d? In that case, this final distance, the image distance, would be d, and that is what is drawn here. I don't understand why they've purposefully made it to coincide with 2f. That doesn't need to be true. 2f could be here, or the image could be anywhere as it relates to 2f, but the image is at a distance of 25 centimeters, at a distance of the least distance of distinct vision. In that case, we need to find out the angular magnification. So here in this case, the magnification would be h by u, angular magnification, right? Because the angular magnification produced by this image is the same as this angle, right? Because these two triangles, now we haven't kept it at the focus, now we've kept it at a distance u. This is the distance u, and these two triangles you can see are similar. So this by this distance will be the same as this by this distance, and this height is h and this distance is u. So it will be h by u by h by d, which is equal to d by u. But we are not done yet because we don't really know what u is. And for that we can use the standard lens formula. We know that 1 by v minus 1 by u is 1 by f. So 1 by, what is v? V here is minus d, right? Because the image is formed at the least distance of distinct vision towards the left side. So 1 by minus d minus 1 by u, that becomes actually plus 1 by u if we take u to be a positive quantity, because minus u would be the quantity with sign, is equal to 1 by f. What does that give me? You take this here, 1 by u is equal to 1 by d plus 1 by f, or d by u is equal to d by f plus 1, right? So this is equal to d by f plus 1. By the way, let me just first tell you the standard definition for angular magnification. It is equal to theta by theta naught. Theta is the visual angle subtended by the image. Theta naught is the visual angle that would be subtended by the object if it was kept itself at the least distance of distinct vision and there was no microscope anywhere. And that's what we've done. Theta is the visual angle, here it's h by f, here it's h by u. And theta naught is the visual angle that would be made if the object itself of height h was kept at a distance of d and there was no lens anywhere. In that case it would be h by d. We see that in the second case the magnification is greater than in the first case, right? But on the flip side, in the first case the eyes are less strained and the second case the eyes have maximum strain. So it depends on what we really want. If we want a greater magnification and we are willing to compensate that by a huge strain on our eye, then we'll use this, in which the image is formed at D. But if we don't want any strain on our eyes, then we'll use this where the eyes are least strained because the image is formed at infinity. Right. Now let's look at the second case, which is more complicated than this, and that is the compound microscope. In a compound microscope, we don't only have one lens, we actually have a combination of two lenses. So this is the image for a compound microscope. It has two lenses. One is called the objective lens, the other is called the eye lens, or more generally for your course, it's called the eyepiece. Right, and sometimes it's also called the ocular. And the eyepiece is the lens that's closer to the eye. So here is where your eye would be looking at an image. Right. For a compound microscope, the eyepiece has a greater aperture than the objective. This is the opposite of what will be true for telescopes. So you need to remember this. For microscopes, the aperture. Aperture basically means the size. We've talked about it. It means the diameter of the circular boundary of the lens. Basically this whole height. So the aperture of the eyepiece is greater than the aperture of the objective. Now we keep an object in front of the objective lens. It creates an image, and now this object is not between the pole and focus. It's actually beyond the focus. If it was between the pole and the focus, then we would have a virtual erect image made behind it, like a simple microscope. We don't want that. We want it to create a real and inverted image at a certain distance, so the image is created here. Now the design is such that, and in fact most microscopes and telescopes are such that this distance between the objective and the eyepiece, which sometimes is called the length of the microscope or the telescope. Telescopes also have objectives and eyepieces, they're pretty similar. So this total is called the length, and this can be changed continuously. You've seen features in telescopes, I'm sure, where you can push it in and the length of the telescope decreases, pull it out and the length of the telescope increases. Right? So this length can be varied continuously. And it is designed in such a way that the image formed, I1, the first image formed of this object, lies between the pole and the focus of the eyepiece. If it lies between the pole and the focus of the eyepiece, then it will create a virtual, enlarged, erect image here. So ultimately we have two magnifications. First magnification is created when O makes an image I1 and I1 makes an image I, that is the second magnification. And for the total magnification, we'll have to take care of both of these magnifications. Let's label a few things here. By the way, every labeling I'm doing is a purely positive quantity, and in the equations we'll take that with sign. So this distance is what I'm calling U0, UO, U of the objective. In the equation we'll take minus UO, this is the length between these 2 points. This is called VO, or the position of the image for the objective. This is called UE, or the object distance for the eyepiece. And this distance, I'm not going to label it, it will make the figure messy, I'll just label it maybe here. This distance is called VE. Right? Now all of these are positive quantities. This distance is FO, the focal length of the objective. This distance is FE, the focal length of the eyepiece. Now what is magnification? We know that it will be theta by theta naught. And we already know what theta naught is. It is h by d. Theta naught is the angle, is the visual angle produced if this object itself was kept at the least distance of distinct vision and there were no microscopes or lenses present. In that case, it will be h by d. This is like the object distance for a standard lens system, right? What is the magnification? It is the height of the image by the height of the object, or you could say the height of the image divided by the original height. So h by d is the original visual angle if there was no microscope present, Right. Now we need to find out theta, which is the angular magnification produced for the compound microscope. So now the final visual angle will be this height. Let's say this height is h, this is h dash, this is h double dash. This height h double dash divided by VE. But again, by similarity, we can see that h double dash by VE is equal to h dash by UE. Right. So that's what we'll take it to be. H dash by UE, which comes out to be h dash d by h UE. Now h dash by h, we know what it is. It is minus v naught by u naught. That is the magnification produced by a single convex lens. Minus because h dash and h are taken to be positive. D by ue. Now let's look at this term for a second. D by ue. We got d by u as the magnification for a simple microscope when we put the image at d, and in that case magnification turned out to be 1 plus d by f, which was d by u. So we can write this magnification as minus v naught by u naught multiplied by m e. ME is the magnification of the eyepiece, and what is that? It is the magnification produced by eyepiece if it was a simple microscope. Right. So and that is what it is, right? After we inverted the object and made it magnified 1 times, this is basically the functioning of a simple microscope. And for a simple microscope, we don't need to do just this specific case where the image is not formed at infinity. We can do both the cases simultaneously because we've already done them. So this means the magnification for a compound microscope is minus v naught by u naught times d by fe for normal adjustment, or A, and in the case of B, m is equal to minus v naught by u naught times 1 plus d by fe. We know d by f is the magnification for normal adjustment. We can't see that from here because this figure is not drawn for the normal adjustment case. But once we get d by ue, we conclude from that this is the magnification of the eyepiece, which would be d by ue in any case, and which would come out to be 1 plus d by fe. However, for normal adjustment, it would be d by fe. Right. So these are the magnifications for a compound microscope. D is always a universal constant, Fe is the focal length of the eyepiece, V naught and U naught are the position of the object and the first image made by the objective. Now for the objective, we'll have the image, this is by the way image at D. This is the 2 cases we'll do for the telescopes as well in the next videos. First case will be normal adjustment where the final image is at infinity and the eyes are least strained. The second case will be least distance of distinct vision, image at D, where the magnification will be greater but eyes will be strained more. Right. Now we can simplify it a little bit further. For the objective, we know that 1 by V naught, that is 1 by V, minus 1 by U, or you can write it as plus 1 by U naught, because U would be negative, is equal to 1 by FO, where this is the equation for the objective. Right. For the objective, we can get V naught by U naught is equal to, we take this here, multiply the whole equation by V naught by F naught minus 1. And now we'll make a few approximations. The first is that you can see that from the figure as well. We assume that the focal length of the objective is very, very small. So if F naught is very, very small, this term is very, very large, and we can just write V naught by U naught is approximately equal to V naught by F naught, which means minus V naught by U naught approximately equal to minus V naught by F naught. And from that, we can make another approximation, which is that V naught is approximately equal to L, as UE is designed to be small. So we've taken 2 assumptions. This focal length is very small and this length is very small. And generally you can vary the length of the telescope such that these 2 conditions are met. In that case, we can just write this as minus L by F naught. So the equation we get finally is M is equal to minus L by F naught D by Fe in the first case normal adjustment, and minus L by F naught 1 plus D by Fe in the second case. Now notice what we've done here. Everything is now independent of V and U. L is what the length will be for a particular microscope at a particular time. F naught and Fe are fixed and D is fixed. So we get fixed magnifications for both the cases. This completes our study of microscopes. In the next video, we'll study 3 different kinds of telescopes: the astronomical telescope, the terrestrial telescope, and the Galilean telescope. Thank you.